we will do it like means in very easy way, and each and every point means I will clear basics, and will tell you that what type of questions that can be asked from the chapter, that we will also discuss here. So firstly, I will explain here that what is equilibrium. Before starting the chapter, it should be clear that what is equilibrium basically. So, do you have any idea equilibrium? What is equilibrium? Okay, okay. Hmm, hmm, hmm. Okay. So I will tell you in very simple way. So means as you are just mixing the things, you are mixing like this thing that it is dynamic in nature. So these are its features. These are its characteristics actually. So what is equilibrium basically? How we can define equilibrium? So we say that equilibrium is a state where the rate of forward reaction is equal to rate of backward reaction. So in very simple words, I can write here this thing. You can also write in your notes. Equilibrium simply means the condition in which rate of forward reaction, or I can say it is the state when rate of forward reaction, or I can say forward reaction rate is equal to what? Rate of backward reaction. So this is the equilibrium state. So for example, we have two types of equilibrium actually. First one type of equilibrium that we have: physical equilibrium. Physical equilibrium. So physical equilibrium, in case of physical equilibrium, as the name itself indicating, this is the equilibrium seen in case of physical processes, or I can say like any physical process. Like for example, let's say I am writing this physical process. Water changes into steam. So water is in the liquid form. Water is in the liquid form, and it is changing into the steam, means it is changing into the gaseous. Right. So whenever I am showing arrow towards this direction, so this is the forward, and whenever I am saying reverse arrow, so this is backward. Yeah, this is backward. So physical equilibrium, so which is seen in case of the physical processes. What about chemical equilibrium? Whenever we are saying about any chemical reaction, basically, so equilibrium set up in the chemical processes. Yeah, a new substance is being formed here. Haber's process, for example, N2 plus 3H2 will give you 2NH3. This is the Haber's process for the formation of what? Ammonia. So see here, NCERT paragraph states one thing. So I will share here book, and also you underline in your books. I will tell you important points that you can underline there. Yeah, so this is the NCERT page. So here you can see one example is given. One example is given: rate of evaporation. So this is the equilibrium in case of what? This is the case of what? Physical equilibrium. Is this the case of physical equilibrium? Yeah. Here the rate of evaporation is equal to the rate of condensation. Yeah, so liquid to vapor, that is vaporization, whereas reverse of it, that is condensation. So yes, so this thing you have to underline: equilibrium can be established for both the physical and chemical reactions that I told you. The reaction may be the fast or slow depending upon the experimental conditions and the nature of the reactants. So what is the dynamic equilibrium basically? So what do you mean by dynamic equilibrium? This thing we will clear from here first. Do you have any idea what is dynamic equilibrium? Yeah, right. So, in very simple words, I can say that if a dynamic equilibrium is a condition in which the forward reaction continues and backward reaction also continues, but both happens at the same rate. Both happens at the same rate. So that means what? That the concentration becomes constant. Concentration become constant, obviously. So this is the means reaction is not stopping. Reaction is in the dynamic. Okay, dynamic means moving, it is moving, that is not stopping. So this is meaning of dynamic equilibrium. So this thing we understood. So now here chemical equilibrium, so that thing already I told you. So now here directly we will move here, we will also study here ionic equilibrium. So here there is the first heading, that is equilibrium in physical processes. In the physical processes I told you one thing, that there is what, phase transformation processes, like solid to liquid or vice versa, liquid to gas or vice versa. Yeah, only state of matter. So for example, there can be solid liquid equilibrium, there can be solid liquid equilibrium, okay, and there can be the liquid vapor equilibrium. So in all these you can see what is there, state change is there, and equilibrium is being established, like solid to vapor equilibrium is there. So now we will discuss here very important point, which is the, underline this point from here, Henry's law. Underline, very, very important, Henry's law. So, yeah, this thing. This is Henry's law. Henry's law states that mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. So what does Henry's law states? This states that mass of a gas dissolved in a given mass of a solvent at any temperature, whatever the mass of a gas you are taking, whatever the mass of gas we are taking, so the mass of a gas dissolved in a given mass of a solvent at any temperature, that is proportional to what, pressure of the gas above the surface of the solvent. So what does Henry's law states? Henry's law simply states that the, tell me. Okay, or see mass of a gas is directly proportional to what, that is directly proportional to the, that is directly proportional to the pressure of the gas above the surface of the solvent, or I can also say mass of gas, or I can also say amount of gas dissolved. So what does it mean? In very simple words, it means that if there is more pressure, as it is directly proportional, so it simply means that if there is more pressure, then more gas dissolves, then more gas dissolves, obviously, because it is directly proportional, that amount is directly proportional. And also if there is less pressure, so it means less gas dissolves, it simply means that less gas dissolves at that case, right? So if I see its formula in mathematical term, it is P is directly, very easy, P is directly proportional to what, x, okay, P is directly proportional to what, x. So this is the formula. So see, whenever you have to study any formula, you have to means write its meaning also, that what does the symbols are going to indicate. So here P is what, that is the pressure of gas, that is pressure of gas. X is equal to what, that is mole fraction. X is equal to what, mole fraction of the gas in solution. Mole fraction, small x is what, mole fraction. And see, when I remove this proportionality sign from here, when I remove this proportionality sign from here, It is equal to kh. Kh is what? Henry's constant. K, below it I am writing this h. So this is what? This is the Henry's constant. Okay. So P is equal to what? Kh multiplied by x. Understood? Tell me. Kh multiplied by x. So this is the thing that your P is directly proportional to what? P is directly proportional to x, and P is equal to kh multiplied by x. This we have to remember. The amount of gas which is dissolved, that decreases with the increase of temperature. That decreases with the, means it is inversely proportional to what? Temperature, whereas directly proportional to what? Yeah, directly proportional to the pressure. This is the main point. And example, the soda water bottle is sealed under pressure of a gas when its solubility in water is high. So question can come. So cold, what is the example? So this one, soda water bottle, that is sealed under high pressure of a gas. Or I can say, in simple words I can say, in the exam I can write the example, cold drink bottles. So here in these, CO2 is dissolved, CO2 gas is dissolved under high pressure. So this is the application part actually. And application part is, it is used in case of example, cold drink bottles, in which CO2 gas is dissolved under the high pressure. Under pressure of a gas when its solubility in water is high, because the solubility that depends upon what? Pressure. It depends upon the pressure, I told you already. So here, very very important part. See, this part start from here, very very important. General characteristics of equilibria involving physical processes. This is very important. So this we will discuss here. So now we will discuss here this thing that I'm saying, general characteristics of equilibria involving physical processes. So what are the general characteristics that we have here? First is, equilibrium is possible only in a closed system at a given temperature. Equilibrium is possible in what type of system? In a closed system. You might have studied in the thermodynamics, we have open system, we have closed system. So like this. So it is possible only in which type of system? Only in the closed system. And yeah, so this is the first general characteristic. And second, both the opposing processes. Which opposing processes I'm saying? Forward as well as backward. Forward as well as backward reactions. So these are the two opposing processes. So these occur at the same rate, and there is a dynamic. I told you already that there is a dynamic but a stable condition. So that thing, a dynamic equilibrium thing. And all the measurable properties of the system remain constant. What measurable properties I'm saying? Like temperature, like pressure, which we can measure. So those properties, all the measurable properties of the system remain constant. So when equilibrium is attained for a physical process, it is characterized by the constant value of one of its parameters at a given temperature. So basically, main things what you have to understand, that it takes place in a closed system. It takes place in a closed system. Then, secondly, you have to remember that all the measurable properties of the system remain constant. So, I will tell you how you can write this in the exam. So, I will write it in very easy way. You can write in your notes. So, general characteristics. First point: what are the general characteristics of equilibria involving physical processes? Write down first point: both forward and backward, both forward and backward processes occur simultaneously. For example, let's say I'm saying ice to water. This is forward, this is backward. So that is ice melts forward, whereas our water that freezes. So that is backward reaction here. So both keep happening, both keeps on happening. This is the first one. Second one is your word, that is rates of forward and backward reaction. Rate of forward and backward processes, here I'm saying processes that become equal. In case of physical equilibria, that becomes equal. So in this case I can say that at equilibrium here, for this example if I'm saying, so I can say rate of melting is equal to rate of freezing, or other examples can be like rate of evaporation, that is equal to rate of condensation. Rate of evaporation is equal to rate of condensation. Next, equilibrium occurs, third point, equilibrium occurs only in a only in a closed system. Equilibrium occurs only in a closed system. Okay, and next point, at equilibrium measurable properties become constant. Yeah, yeah. Like density, like mass, these properties I'm saying about, these are also measurable properties, right? So in very simple way we discussed the general characteristics of equilibria involving physical processes, right? Like your pressure, so like concentration, this can be the measurable property. Then your density, this can be there, or your mass, your temperature, your volume. So, in one line, I can say that at equilibrium, measurable properties like pressure, concentration, mass, density, etc., they remain constant. Understood? Any doubts? Okay, fine. So, general characteristics, whatever we have to means remember that I discussed. So now here I can discuss here this one, law of chemical equilibrium, very important. Law of chemical equilibrium, this one very very important. So you have any idea of law of chemical equilibrium, Ahana, or no? No, no, Lee Chatelier principle, separate thing. No problem. Okay, okay, it is very easy, you just see here carefully, you can clearly understand. So our topic of discussion is law of chemical equilibrium and equilibrium constant. So I can write here its definition. I think it is given. See, in this page it is given. You can just underline. I am just sharing you. This is given, Ahana. This one you found this. This page is according to my textbook. It is page number 193. Hmm, hmm, hmm. Yeah, this is the law of chemical equilibrium. So now I will explain it in very easy way. So see what it is exactly. So law of chemical equilibrium. At a given temperature, the product of concentration of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentration of the reactants raised to their individual stoichiometric coefficient has a constant value. Means in very simple way, it means that at a given temperature for any reversible reaction, whenever I'm saying for any reversible reaction means the reaction which can be reversed, means forward and backward. So this is given a little bit confusing here. So that's why I'm writing its easy definition. You can write in your notes also. Law of, yeah, law of chemical equilibrium. So I'm writing here. You can write along with me. So at a, is my screen visible? Am I clearly audible? Okay, fine. So at a given temperature for any reversible reaction, at a given temperature for any reversible reaction, the ratio of the ratio of the product of the ratio of product of equilibrium equilibrium concentration equilibrium concentrations of the products to the product of equilibrium concentrations of the reactants, each raised to the power each raised to the power of their respective stoichiometric coefficients stoichiometric coefficients. I will explain this equation after this. Okay, I'm just reading it once. See, I am just explaining it. So first I will explain step by step. See, at a given temperature for any reversible reaction, for example, I will give you an example. For example, I am writing this reaction. Let's say a of a plus b of b. Here I am showing this reaction toward the forward side. Okay, here I am showing it toward the backward side. So a of a plus b of b will give you c of c plus d of d, let's say. Okay, so what I'm saying here, at a given temperature for any reversible reaction. So this thing you understood, Ahana. Reversible means it is forward, it is backward. Okay, so see the ratio. Yeah, so I will tell you step by step, no problem. The ratio of the product of the equilibrium concentration of the product, what I am saying, What I am saying, I am taking two ratios here. What ratios I am taking? Concentration of what? Products to the concentration of reactants. Tell me, in this reaction, what are the products? C and D. So C and D are the products, right? So concentration, keep in mind that concentration we write, whenever we express the concentration, we write it in the square bracket form like this. For example, if I have to write concentration of C, I will write in this square bracket C. Concentration of D, like this. So ratio of what? Reactants. Reactants are what? A and B. They are the reactants. So see, now coming to the statement, the ratio of the product of the equilibrium concentration of the products to the product of equilibrium concentration of the reactants, or I can also say like this: product of the concentration of the products to the concentration of the reactants, that ratio. And I am saying what? Each raised to the power of its stoichiometric coefficient. See, what is the stoichiometric coefficient of A? Small a. What is the stoichiometric coefficient of A? Small a. So this is in this form, raised to the power, like this. And B, what is the stoichiometric coefficient of this B? This small b. Then for this C, this is this small c. For this is small d. So in this way, this ratio is constant. This ratio is constant. This is the law. Yeah, this is the formula for the equilibrium. This is the law that these ratios are constant. This is the law. Okay. So on the basis of this, we can write what? Equilibrium constant. We can write what? Equilibrium constant. So this formula is basically for what? Kc. Kc is what? Kc is what? That is equilibrium constant. Here Kc is what? That is the equilibrium constant. Understood? Tell me. Sure. In your textbook you can underline, see the thing that we discussed now. So that has been explained here in a very easy way. See, A plus B, this is the reaction. A plus B will give you C plus D. So in this equilibrium, if you have to write the equilibrium equation, you have to write the equilibrium equation for this equation, let's say. So how you can write? Here there are no stoichiometric coefficients. Here there are no stoichiometric coefficients. So Kc is equal to what? C, concentration of C into concentration of D, divided by concentration of A multiplied by concentration of B, where Kc is what? That is the equilibrium constant. That is the equilibrium constant. And this expression on the right hand side here, that is called as the equilibrium constant expression. That is called as what? Equilibrium constant expression. Understood, Ahana? Tell me. It's easy. Hmm. Yeah, yeah, yeah. Yes, yes, yes. So this is the only thing. So mm, whatever the unit of the concentration, what is the unit of concentration? No, units of concentration. So you might have studied in chapter number 1 some basic concepts of chemistry. Have you studied that chapter, some basic concepts of chemistry? So there we have various concentration terms. Yeah, so what is the unit? What is the unit of concentration? So concentration terms are like in terms of molarity, in term of molality. Those are the right. For example, if I'm saying about molarity, then mole liter inverse, like this we take mole liter inverse. Okay. So So here, see, underline this point. The equilibrium equation is also known as law of mass action. The equilibrium equation is also known as law of mass action, and the concentration was called. This one, yeah. And equilibrium equation is also called as what? Mass of law of mass action. Law of mass action. And concentration was called as what? Active mass. Concentration was called as a active mass. So here they are giving an example. Let us consider the reaction between gaseous. You have H2 whenever in the bracket G is written, so means they are in the gaseous form. So let us consider the reaction between gaseous H2 and I2 carried out in a sealed vessel at a 731 Kelvin temperature. Then it will give you, you can see, 2 Hi. So here how many moles are there? 2 moles. How many moles are here? 2 moles are here. So what I want to tell you that, hmm, yeah, so this thing I want to tell you, this will be more clear here. See, this one that I underlined here, can you see stoichiometric coefficients? You can see here. So if 4 is in the multiplication, then this is the coefficient. Okay, here products divided by what? Reactants. So here in this thing, in this case also you can see H2 plus I2 will give you 2 Hi. Here you can see Kc, Hi2 divided by H2 into this I2 concentrations. So equilibrium constant, underline this thing, equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. For example, let's say this is the forward reaction, this one that I am highlighting here with the green color. This is the forward. This is its backward now. So if I am saying in above equilibrium constant is Kc, let's say. So in order to differentiate, I can write for the second one what I can write. Kc dash, let's say. No. What I'm saying you that, for example, equilibrium constant for this reaction is Kc. So for the second one, equilibrium constant, I can write Kc dash to differentiate. So it means Kc dash is equal to 1 by Kc. Means for the reverse reaction, equilibrium constant for the reverse reaction of the equilibrium constant for the reaction, it is the inverse of what? Equilibrium constant in the forward. Easy, very easy. Yeah, just inverse na. Here you can see reverse. Any doubts? Okay. So here I will tell you this thing. Uh, yeah, you can see one question here, one problem here in the textbook. This is the problem. Let's say here they are giving you the following concentrations were obtained for the formation of NH3. So in this question, they are giving you what? And 2 in the bracket, this like this, so means concentration is given for a and 2, and for H concentration is given. So they are saying about a very famous process, which is the Haber's process. Its equation we know. So how we can write here Kc? Yeah, that is included. Okay, fine. So in this way, we have to put the values and we have to do accordingly. And in the next question also, you can see at equilibrium, the concentration is again given and in a sealed vessel. So they have given you this equation. See, so here what is the product? N2. So if concentration will be NO2 here, divided by here, this is N2 into O2. So you have to put the values and understood. Okay, fine. So next is your what? Next is the homogeneous and what is the homogeneous equilibria and what is the heterogeneous equilibria? So see, as the name itself indicating homo means same. So in a homogeneous equilibria, all the reactants and products are in the same phase. Same phase means what I'm saying, either I'm saying solid, liquid, or gas. That thing. Yeah, that thing only. So you can see in this example is all states are same. So how you can write that what is the homogeneous and heterogeneous equilibrium? So if they ask you the difference, then you will write all the reactants and products are in the same phase. All are gas, all are solids, or all are liquids, for example. So all the substances are in the same phase. Whereas in case of heterogeneous equilibria, reactants and products are in the different phase. That is what, that is the, always keep in mind that only gases or liquids, they are included in the equilibrium expression. Solids are not included in the equilibrium expression. I mean to say here, I will give you example. Let's say, to clear this thing, what I'm saying. So let's say I have reaction CaCO3. Here in the bracket it is written S means solid. Then I'm writing here, this is the decomposition reaction. Decomposition, when it is decomposed, so it will form your CaO, solid phase, plus CO2 in the gaseous phase. Okay, so here you can see one thing, that when I have to write here, let's say I have to write here case C, means I am writing what? I am writing complete equilibrium expression here. Complete equilibrium expression. Firstly, you tell me, this is a case of heterogeneous equilibrium or it is a case of homogeneous equilibrium? Heterogeneous equilibrium. So case C, I will write here case C like this. Case C is equal to CO2, only this. Solid, yeah, solids we do not include. We include liquids or gases. Yeah, understood now what I'm saying? Yeah. Hmm. Yeah, yes. So we will see here in the text too. See, so it is given here. So here, equilibrium constant for in gaseous systems. So we have ideal gas equation. Underline this. PV equal to nRT. We know ideal gas equation, where P is the pressure, V is the volume, N is the number of moles. Number of moles of gas. R is what? Gas constant. T is what? Temperature. So I have this equation, PV equal to nRT. If I will rearrange this equation, let's say I will rearrange this equation. So I will write here P. P will be equal to what? N by V multiplied by RT. Is this clear? Just rearrangement. So here N by V is what? That is equal to C. Means concentration is expressed in this form. Concentration is expressed in this form. Okay. You know N by V equal to what? C. Means concentration. Any doubts? So Hmm. Yeah, P equal to CRT given in the book. This one underline. So we can also write here in the bracket gas into RT, which is written here. So whenever I am writing within the square bracket, I am writing this gas. So means it means I am writing the concentration of gas. I am writing what? Concentration of a gas. So R is what? Yeah, yeah, for gas only we are discussing here. Obviously, our heading is what? See, our heading is equilibrium constant in gaseous systems. So, what is the value of R in terms of bar liter? So, it is 0.0831 nearly gas constant value. So, here, for example, I have to write case C for this reaction. This one you understood. This one. Hmm. So this thing we understood. Case C we can write in this way. So here, see, underline this thing. At constant temperature, the pressure of a gas is proportional to its concentration. The pressure of a gas is how it came. It is very interesting. As our equation was what? P equal to CRT. Yeah, then we just rearranged it. PV equal to nRT was there, na? PV equal to nRT. Then as I told you that N by V is equal to concentration. So after that we wrote it as P equal to CRT. We wrote it as. So it's very easy. So by this we came to know what we came to know, that pressure is directly proportional to what? Concentration. Is it? Okay, so very easy. So accordingly we can do here. So here it is written P is directly proportional to, if it is written in the square bracket, so means I'm saying about the concentration of what I'm saying, concentration of a gas I'm saying here. So so may I write that? Yeah, tell me. Yeah, I am just explaining that part. It's very easy. See, as I told you, P equal to CRT, I told you this thing. Means I am saying about the concentration of gas. So, may I write here the concentration? So, yeah, means I am just substituting in this equation. I am just substituting it in this equation. What is the concentration here for this one? First one is what? HI. So concentration of HIC, I am putting here the value in term of this PCRT. Understood, Ahana? Our equation was what? P equal to CRT. Okay. So here, for example, I have to write P for HI. Okay. So what will be the concentration here? Is this HI is the concentration here, because I told you that whenever I will write in this bracket, square bracket, so it means concentration. Okay, so I if I have to write P for HI, then it will be what? HI. Yeah, pressure. HI for HI. Pressure of the gas I am saying, na? So pressure of which gas? HI. So concentration I will write here, that is HI multiply by RT as it is in the formula. If I have to write PI2, tell me how you will write PI2. Hmm, right. PH2. Yeah, now it is very interesting. See, so as we came to know here that what we came to know here that maybe right here what thing I told you, that pressure is directly proportional to what, concentration. So this thing represents what, that I am underlining with the green color, that represents the concentration. So what I am saying, concentration is directly proportional to what, pressure. So may I write here pressure in terms of this concentration? So I can write here concentration of HI. And again, I will write here with the normal bracket, not in the square bracket, because I am not telling about the concentration here at this point. Any doubt? Okay, 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 okay. Wait. I am just erasing this thing and explaining in the blank slide. What I am saying you, I am saying that pressure is directly proportional to what, concentration. Understood? At constant, for what I am saying, gas. At constant temperature, pressure is directly proportional to what, concentration. Okay, so see, yeah, so if I have Kc, let's say Kc equal to Hi 2 divided by H2 into I2, this is I am having, let's say Kc. So the thing that I am encircling here, what it is representing, it is representing the concentration of what, Hi. It represents the concentration of Hi. So I am saying that pressure is directly proportional to concentration. Okay. So means in terms of this concentration, I can also write pressure of Hi. I am saying what? As I told you that this Hi is representing what? Concentration of Hi. So also I am saying at the same time, I am saying that pressure is directly proportional to concentration. So, what does it mean? It means that in place of this concentration, I can also write pressure for HI. Getting my point? It doesn't mean that they are the same values, na? It doesn't mean. But here, see, we can write this Kc in two terms. Means what I'm saying here is or. It is written or, na? I'm not saying that it is same value. Here it is written or, means if I have to write this in terms of pressure, then we can write in this way, means as they are directly proportional to each other. So we are not substituting the value, but if we have to write the value of Kc in terms of pressure, then we can write in this way. This is what we are saying. So this will be more clear to you when you come to know about, you know what is Kc and Kp. See why this confusion arises, because firstly it should be clear that what is Kc and Kp. These are very important things, so that your all confusion, this confusion that you ask, that will be also more clear. So Kc, note it down, very important. Equilibrium constant in terms of, in terms of concentration. Noted. Equilibrium constant in terms of concentration. Kp, step by step if you will do, you will understand each and everything. Kp is equilibrium constant in terms of pressure, in terms of pressure. So example, our reaction is A of A plus B of B will give you C of C plus D of D. Then here Kc is equal to C of C into D of D divided by A of A into B of B. But for the same reaction, Kp is equal to that thing you asked, na, that is particularly in terms of pressure. So more correctly, we can write it as Kp. Yeah, more correctly. Yeah. Means they just wrote Kc. Just they wrote Kc because Kc is like same as Kp, but it is represented in terms of pressure. That is main difference. So again one thing. So here pressure we will write in the normal bracket, not in the square bracket. So Pc raised to power will be same thing into small c into Pd raised to power will be D divided by Pa raised to power will be A into Pb raised to power will be B. Understood? Tell me. Okay. What is the difference between Kc and Kp? Yeah, remember a relation. A question can come. Next heading you can give relation between Kp and Kc. Relation between what? Kp and Kc. So a relationship is Kp is equal to Kc RT raised to power delta n. Here delta n is equal to, yeah, means moles of how you can find out it, moles of gaseous products minus moles of reactants, minus moles of gaseous reactants. So I will give you an example for more clarity. So let's say I have an example, N2 plus 3H2 will give you 2NH3. So here I have to find out delta N, let's say. So here these all are in the gaseous state. So this is an example of homogeneous equilibrium. So here delta N, tell me what will be the value of delta N here? Minus 2. Final answer. Very easy. So Kp is equal to Kc RT raised to power delta N. Derivation is also very easy. Sometimes they can ask, but not very important. So I will explain derivation also in easy way. Okay. So how you have to derive it? You have to start with. You can also make its notes in easy way. I am explaining. So you have to start with a general reaction. You have to write. For example, you have to write for a gaseous reaction. A of A in the gaseous phase plus B of B in the let's say you have A of A in the gaseous phase plus B of B in the gaseous phase will give you C of C in the gaseous phase plus D of D in the gaseous phase. So here you understood A, B, C, D, small a, small b, small c, d. They are the stoichiometric coefficients. So Then you have to write the relation between concentration and pressure. So you will write from ideal gas equation. From ideal gas equation we have PV equal to nRT. PV equal to nRT. So from here P equal to N by V into RT. So in place of this N by V, as I told you, that you can write what concentration CRT. So if I have to write PA, let's say, for that above reaction, so that will be equal to concentration of A multiplied by RT, is it? Then PV equal to concentration of B multiplied by RT. In the same way, PC is equal to concentration of C multiplied by RT. And what about PD? PD is equal to, yeah, hmm, yeah, great. Way. So now next thing, what you have to do, you have to write the, you have to write the expression for KP. Write expression for KP. PC. Great. So it will be like, yeah, that is raised to power in this way. So then, as we also know that our P equal to CRT, this we know. So substitute P equal to, let's say this is equation number 1. This one, let's say. So substitute P equal to CRT in equation number 1. So it will be equal to what? Tell me. Then Kp will be equal to what? Mm-hmm. Concentration of C obviously into, yeah, great. So we can write it accordingly. So how we can write it as, we can write it as in very simple way, concentration of C into RT, and power is coefficient. In the same way, concentration of D multiplied by RT, power is D, divided by, will be same way, reactants. So A into RT raised to power A multiplied by, it is B multiplied by RT raised to power B. So it is Kp. So Kp we wrote, and Kp we wrote. So any doubts up to this point? So in this way we got this equation for our Kp. Now write in terms of, if I have to write in terms of Kc for same reaction, then it is Kc is equal to concentration of C raised to power C into D raised to power D divided by A raised to power A into B raised to power B. This is like this. So also we know one thing. What we know, that delta N will be equal to what? C plus D minus A plus B, is it? Like this? means change in, because delta n is what here, change in, or more specifically I can write delta ng, means change in moles of gas, change in moles of gas. So the equation that we got, the equation that we got for kp, we can simplify that. In the above also we can simplify that equation. We can just separate. How we can simplify? We can separate concentrations and RT separately, separate concentrations and RT to simplify the equation. So that will be like this: concentration of C, then D multiply by RT, C plus D raised to power we can write, divided by concentration of A into B into RT raised to power A plus B. Just check this step and this step first, this one. And in this step what I did, I am just separating the RT and concentration. Understood? This is easy. Yeah, okay. So also we can write it as Kp is equal to C of C into D of D divided by A of A into B of B. So multiply by into RT. So C plus D minus A plus B. Is it like this? Reactants minus product. Yeah, very easy. Yeah. So by this, what we came to know? Therefore, Kp is equal to Kc RT raised to power delta n. Check whatever is left. Just tell me anything left to note down. Understood the relation? Any doubts to remember anything? Then ask. Okay, great. So there is a numerical problem here related to the Kc. Firstly, we will see that question, which is related to the Kc. Here you have given in this question PCl5, PCl3 and PCl2 are at equilibrium at 500 Kelvin and having concentrations 1.59 molar. PCl3, what is given always whenever you have to solve the numerical problems, you have to see what is given in the question and accordingly you have to use the formula. So concentration of PCl3 is given and concentration of Cl2 is given and PCl5. So equation is also given. So how you will write Kc? Yeah. So in this way we have to do. So heterogeneous, I told you, in this all are in the different phase. H2, like this is liquid, this is gas. So see, if I am saying finally I am writing for this one Kc is equal to CO2. If in the final case I am writing like this, then Kp will be equal to what? PCO2. Kp will be equal to PCO2. Same thing that I told you previously. No, in the equilibrium equation, we don't multiply it. We multiply it whenever we were writing that equation. P equal to that equation, na? That P equal to CRT in terms of pressure. No, no. See, I will simplify. See, your Kc is the equilibrium constant in terms of concentration, whereas Kp is the equilibrium constant in terms of pressure. Kp is the equilibrium constant in terms of what? Pressure. Okay. So, in the equilibrium constant equation, our main thing is what we have to write. What we have to write in the equilibrium equation. For example, this was the equilibrium equation. This one was the equilibrium equation. Let's say we have to write the concentrations here in the case C. And yeah, I understood what you are asking particularly. See, our Kp will be equal to this one only in terms of pressure. But when we then after in the next step, na, we substituted it in term of concentration. So that's why we wrote there CRT. That's why we wrote. Okay, but otherwise Kp will be like this way only in terms of pressure. Whenever we write equilibrium expression, Kp equal to Kc. Yeah, in the same way. But difference is like what is the difference? One is expressed in terms of concentration, other is in term of pressure, and it is same. And here, as you know, that we were substituting the values P equal to CRT, that one. Any doubt? So here you can underline this example also here. This example, let's say you have Ni plus 4CO will give you NiCO4. So here Kc is equal to NiCO4 divided by. So here you didn't mention solid. You can see solid is not mentioned here. Also in this example, you can see Kc is equal to AgNO2 divided by HNO3 twice. Mhm. So, Hannah, you know about the reaction quotient? This one? Okay, fine. So, we will write it in very easy way. What is reaction quotient? Its notes we will make first. So, our heading is reaction quotient. It is denoted by Q. It is denoted by Q. or QC. QC when I am representing it with the molar concentrations, and also I will express it with QP when I will express it with QP with partial pressures. With partial pressures, I will express it as QP. So, however we write, remember Q is equal to KC, means what I'm saying, that you will write it in the same way as that of KC. For example, you have A of A plus B of B will give you C of C plus D of D. So here Q is equal to concentration of C into D raised to power D divided by concentration of A raised to power A into concentration of B. Understood? So in the same way you have to write. It is the ratio of the concentration of products to the concentration of the reactants with raised to power. Same. Yeah, basically what? Yeah, basically KC. Now, yeah, heterogeneous equilibria. In heterogeneous equilibria, you have to study the definition and example that I did. Let me show you it once. What I did. This is the definition. Equilibrium in a system having more than one phase is called heterogeneous equilibria. More than one phase. So the equilibrium, yeah, solids are not included. So then, yeah, they wrote like this. This thing I want to clarify. They write this, but after that, in the modified form they wrote this one. So you have to remember this one. Just underline this. So and also underline this thing. For example, they are giving in this example H2O give you gas. So in this example, there is a gas phase and liquid phase. In the same way, equilibrium between a solid and its saturated solution. So, for example, you have calcium hydroxide plus aqueous. Aqueous means solvent is water. So ions you will get in the aqueous solution, Ca2 positive ions. So, but here one thing is there, that solid and aqueous. So phase is different. So this is the equilibrium between the gas and the liquid phase actually. And next you have to underline this one. Heterogeneous equilibria often involve pure solids or liquids. It often involves pure solid or liquids. Then after that, underline this thing, we can simplify equilibrium expressions for the heterogeneous equilibria involving a pure liquid or a pure solid, as the molar concentration of a pure solid or liquid is constant. Underline this thing. Molar concentration of pure solid or pure liquid is constant. Means, what does it mean? It means that it is independent of the amount present. Means, hmm, yeah, yes, yes, concentration. So means it doesn't depend upon the, like, here they are giving the example on the amount, independent of the amount present. So then this equation and this final equation you can write, you can remember. Then in terms of pressure that I told you. And one more example, this example you can remember. This example, equilibria between the nickel and carbon monoxide, CO. And what is formed here? As it is 4CO. So which compound is formed here? Nickel carbonide. NiCO4. NiCO4. Understood? This you have to remember. No need to confuse more. Just examples and definition. Then after that, this thing I will tell you what you have to remember. But first I was discussing the important topic from here, which was what? Reaction quotient. So reaction quotient is what? Ratio of the. Now is this question coming in your mind that then what is the difference between reaction quotient and equilibrium constant? I think this question is coming in your mind, because as we are writing these in the same way, so what is the difference? So you can write here the difference for more clarity of the concept. Okay, so in one side you can write reaction quotient, in other side you can write what? Equilibrium constant. So whenever I'm saying equilibrium constant means I am saying about Kc or Kp. So equilibrium constant and reaction quotient. So reaction quotient is the ratio of products to reactants at any time, at any time. Understood? At any time. Whereas equilibrium constant is a ratio of products to reactants at equilibrium. At equilibrium. This is particularly at equilibrium. Done? So these relations you have to remember. Right here IMP. When QC is greater than KC, reaction will proceed in the reverse direction. Means in the direction of, in the reverse, what is there? Reactants. So when QC is greater than KC, the reaction, direct MCQ can come from here. They can give you that if QC is greater than KC, then what will be the, in which direction your reaction will proceed? In the reverse direction. And in the forward, when just opposite, QC is less than KC. And when at equilibrium, QC is equal to KC. At equilibrium, QC is equal to KC. Here it is given in the end. This also you can write note point. So this is also very easy. Same thing that I am telling, that thing only. Reaction will proceed in the forward. Forward means left to right. Then if it is greater, then right to left. means in the backward. And when both are equal, then equilibrium. Yeah, equilibrium state exists there. So in the reaction question topic, what you have to learn, the definition, formula, these conditions, only this one. Then next, very very important topic, next, which is the important topic that I will share here. So yeah, this one, relationship between equilibrium constant K, reaction quotient Q, and gives energy. Relation between K, that is equilibrium constant, reaction quotient Q, and gives energy is capital G. So I will give you its easy notes. You can write in the formula form in your notes. First you can write, so first I am writing here what, relationship between what, gives energy and gives free energy and reaction quotient. A reaction quotient is denoted by what? Q. Gives free energy, G. So for a reaction at any moment, means I am not saying at equilibrium if I am dealing with reaction quotient. So for a reaction at any moment or at any time, delta G is equal to delta G naught plus RT ln Q. So here delta represent what? This delta represents what? It represents change. Easy. So here delta G is equal to gives free energy gives free energy at that moment, and delta G naught, whenever this naught come, so means we are saying in the chemistry, we are saying under the standard conditions. So delta G naught is equal to gives free energy change under standard conditions. And what about this Q? This Q is the reaction quotient. And what about this R? That is the gas constant. What about this T? That is the temperature. That is the temperature. Okay. So at equilibrium, delta G is equal to 0. At equilibrium, delta G is equal to 0, and also Q equal to K. I discussed with you Q equal to K. K is what? equilibrium constant. K is equilibrium constant. So we had the equation delta G is equal to delta G naught plus RT RT ln Q. This was our equation or not? Yeah. So at equilibrium, this equation can be written as 0 is equal to delta G naught plus RT ln K. Understood? Tell me. Ln is natural log. So I can rearrange it as delta G naught is equal to minus RT ln K. This is the relationship between, this is the key relation between delta G naught and K. This is the key relationship between delta G naught and K. So this we have to do. Delta G naught is equal to minus RT ln K, natural log K. Natural log value. So a question is given. So you know how to solve the natural log or not? Clear principle. Properly, or I need to give it summary? Okay, okay, fine. In very easy way, I can say that ionic equilibrium is the condition when the ions in a solution stop changing in amount because forward reaction and backward reactions are equal. They are just equal. So ionic equilibrium is when the ions in a solution stop changing in amount because the forward and the backward reactions they become equal. So that is the ionic equilibrium condition. So here what we have to learn, there is the topic here which is important, that is the acids, bases and salts. So you know a definition of acids according to the Arrhenius concept. Yeah, so underline this according to this paragraph. According to Arrhenius theory, acids are the substances that dissociate in water to give the hydrogen ions, and bases are the substances that produce hydroxyl ions, that is OH negative ions. So they are the bases. So then next is the example. So basically acid is a substance that increases the H positive in water. For example, your HCl. So HCl will give you what? H positive plus Cl negative. Base is a substance that increases OH negative. So for example, NaOH will give you Na positive plus OH negative. Na positive plus OH negative ion. So but there are the limitations of this law. So as it is saying that in the aqueous solution. So this is the only limitation, that it is applicable only in case of aqueous solution, because it is simply saying that the Arrhenius acids must produce H positive or OH negative ions in the solution. That it is saying. But see, ammonia is also a base. So will it produce OH negative? No. So it doesn't explain the acid base behavior in a non-aqueous solvents. So this is the case. This is the it. Yeah. Arrhenius does not explain the basicity of some substances like your NH3, because it is only applicable to the in case of aqueous solutions, not applicable to non-aqueous. So this is the, see, if I have let's say I have NaOH, let's say. So obviously this is clear that we will get OH negative here, hydroxyl ion. But ammonia, is ammonia containing, for example, I have KOH. This thing is clear that this will give you OH negative. I have calcium hydroxide. So is it will give you OH? No, because it doesn't have. So now here the question arises that on the basis of what we are saying that it is a base. So this is explained by the Lewis. It is a Lewis concept actually. Lewis concept is basically the electronic concept. It explains that bases are the you know what are bases according to Lewis? Which donates an electron pair. For example, so why they can donate the electron pair? Because they are containing electron pair with it. For example, ammonia structure is like this. This is one nitrogen, three hydrogen are attached, and there is one lone pair of electron. You know, lone pair of electron, that is denoted by the represented by two dots. So as it is having the electron pair, due to this it is basic in nature. So according to the Lewis concept, its basic character is explained. Because of the lone pair. Now, next concept is the Bronsted-Lowry concept of acids and bases. So according to the Bronsted-Lowry concept, your acid is a substance. Acid is a substance that donates a proton. That donates a proton. Okay, so acid is a substance that donates a proton. That is H positive. So proton donor is what? Acid. So see, can you tell me means main differences on the basis of this thing? Means on the basis of the language. As Arhinis is saying that in the aqua solution it give this thing, but Bronsted is saying like they can donate a proton donor. Base is the base is a substance that accepts a proton. For example, we have HCl. HCl plus H2O. Remember, H2O is amphoteric in nature, but here it behaves as a base because in front with it there is acid. So you know that when conjugate acid base pair concept we will discuss. That's another concept here. We will discuss after this. So see, we have here H2O. When the H2O dissociate, that will give you what? H positive plus OH negative. So here, as I told you, base is a proton acceptor. So this base will accept this proton H positive. So it will form what? H3O positive. Whereas this acid had donated its H positive. So basically here it will become Cl negative. Understood? Tell me. So can you tell me if I have to explain the Bronsted-Lowry base concept? So here, can you tell me what will come NH3 plus plus H2O? What you will get here? This is base. This will act as a acid here. Hmm. OH negative, na? Because when the water dissociate, it will form your H positive plus OH negative. So yeah, so plus OH negative. So now we will explain. I will explain a very important concept, that is conjugate acid base pair concept. Conjugate acid base pair concept. So firstly, you can write its definition, Ahana. It will be easy to understand. So conjugate, heading is conjugate acid base pair. Its definition: a conjugate acid base pair, a conjugate acid base pair consists of two species that differ by one proton, that is H positive. And next point we can write in the form of note: when an acid loses a proton, when an acid loses a proton, it becomes its conjugate base. Then when a base gains a proton, it becomes its conjugate acid. So see how you have to remember. Acid will become what? Conjugate base. Acid will become base. Which base? Conjugate. When it will become a conjugate base? By losing a proton. We know na, because acid that loses a proton. So after losing a proton, it becomes a base. Which base? Conjugate base. And base become acid. Which acid? Conjugate acid. After gaining a proton, as base is a proton acceptor. Complete. So we will take an example. I will explain an example here. For example, you have HCl will give you H positive plus Cl negative. Here acid is what? HCl. Tell me what is its conjugate base? H positive or Cl negative? Yeah, Cl negative. It is its conjugate base. Good. Next example. Let's say I have NH3 plus H positive, we will give you NH4 positive. So you have to tell me what is the conjugate acid of this base ammonia. Yeah, good. So means what is the key point? That every acid has a conjugate base and every base has a conjugate acid. Any doubts? Lewis concept also we discussed, that is based on the electronic concept. Ionic product of water. Ionic product of water. So here, Ahana, you have to underline this relationship. This is the example that I told you for Bronsted one. And after that, this thing, conjugate acid base pair, I told you this. And next, some examples are given here. like some problems related to conjugate acid base. Then Lewis acid, this is the definition, underline this. Remember, BF3 is the example of Lewis acid, whereas NH3 is the example of Lewis base. Lewis acids are electron deficient. Lewis acids are electron deficient. Tell me, electron deficient species will have positive charge on it or negative? What do you think? Positive. So Mg2 positive, Cu3 positive. They are what? Lewis acids. Yeah, but there are some neutral also. Neutral Lewis acids also, like AlCl3. Lewis base will have negative charge on it, like OH negative, like ammonia, like water. These are what? These are Lewis bases. Then this is the topic: ionic constant of water and its ionic product. So here this formula you have to underline. This formula: Kw is equal to H positive concentration into OH negative concentration. And underline this: the concentration of H positive has found out experimentally as 1.0 into 10 raised to power minus 7 molar at 298 Kelvin. So Kw, which is the ionic product of water, that will be equal to 1 into 10 raised to power minus 14. That's why if I am substituting here, because as the dissociation of water produces equal number of H positive and OH negative ions, so the concentration will be equal, yeah. So that's why if I am substituting here the value, I will get 10 raised to power minus 14. Then after that, underline this: if acidic substances, then concentration of H3O positive is greater than OH negative. In case of neutral, it is equal. In case of basic, H3O positive is less than OH negative. pH scale. Acidic solution have the pH of less than 7, basic have greater than 7, neutral have pH equal to 7. And this formula, this one, pKw is equal to pH plus pOH is equal to 14. See, whenever water is dissociating, you are getting what H positive and OH negative. So pH, what is the simply what is pH? pH is the negative log of H positive concentration. pH formula, negative log of hydrogen ion concentration. So pOH is what? That is the negative logarithm of if I have to write pOH, let's say, then it is minus log of OH negative. It is minus log of OH negative. So pOH, as you are asking, what is pOH? So it is a measure of basicity. Of course, it is the measure of basicity, as it is telling about what OH, na? Yeah, concentration of yeah. So it is the measure of basicity of the solution. It tells how much OH negative ions are present. If like see, as it is negative logarithm na, so what does it mean? It means that if there is low pOH, then more OH negative ions are there, then it will be a strong base. And if there is high pOH, then less OH negative ions are there, then it is a case of weak base. Means in simple words I can say that POH measures OH negative concentration. Ahana, understood? Tell me. Okay, Ahana. So let's do up to this. And